Have you ever stopped to think about how your phone call, just one among millions, gets through without turning into a jumbled mess? It honestly seems like magic, right? Well, it's not magic, it's math. A brilliant mathematical trick, actually. And today, we're going to break down exactly how it works. So, let's dive into code division multiple access, or as you probably know it, CDMA.
All right, let's frame the whole problem with a simple question. Imagine you have 4 people, all trying to talk on the exact same channel at the exact same time. How do you keep it from just becoming noise? How does anyone hear anything? That is the exact puzzle we're going to solve today.
Okay, first things first. Before we get into the nitty-gritty numbers, let's just get our heads around the big picture concept.
So what makes CDMA so different? Well, other methods might slice up time or slice up the frequency, giving everyone their own little private piece. But CDMA, it does something way more clever. It lets everybody use the entire frequency band all at the same time. The secret? It gives each user their own unique secret code.
Here's a great way to picture this. Imagine you're in a really crowded room, and there are 3 other pairs of people all having loud conversations. It should be total chaos, right? But what if each pair was speaking a totally different language? You could just tune out the languages you don't know and focus only on the one you understand. CDMA is kind of like that, but its languages are special mathematical codes, and they have a property that is, frankly, amazing. We'll get to that.
All right, so that's the basic idea. Now, let's see how these secret languages, these codes, are actually put to work. We're going to walk through a real example. So, in our little scenario here, we've got 4 stations. Let's call them S1 through S4. Each one just wants to send a single bit of data. It's either a +1 or a -1. Now, to do this, the system gives each station its very own unique code sequence. You can see them there on the right, C1 through C4. You can think of this as their secret key. So how do they use that key? It's really just simple multiplication. Let's take station 1. It wants to send the data bit -1. So it multiplies that -1 by every single number in its code. The result? A brand new signal that is -1, -1, -1, -1. And this exact same thing is happening for all the other stations, each creating their own unique signal. Now, this is where it gets really interesting. All 4 of those signals, all created at the same time, are broadcast and added together on one single common channel. And, as you can probably guess, this creates what looks like a total jumble of numbers. And this is what everyone on the network hears. This combined signal, 0, -4, 0, 0. It just looks like random noise. So the question is, how on earth could Station 1 possibly find its original message, that simple -1, buried somewhere inside all this chaos?
And that brings us to the most brilliant part of this whole system, the decoding. We're about to see how we can unscramble this mess and pull one single clear message right out of all that noise.
Okay, so imagine you're the receiver for Station 1. You've just received that combined signal, 0, -4, 0, 0. Your only job is to figure out if the original data sent to you was a 1 or a -1. So, what do?
You use your own key. The receiver takes that jumbled signal from the common channel, and it multiplies it by its own unique code, that same C1 from before. This is the absolute crucial step. It's like using your own personal decoder ring on a secret message that everyone else can see but can't understand. So let's just walk through the math here. We multiply the 2 sequences together, add up all the results, and what we get is a grand total of -4. Then there's one last step. We divide that number by the number of stations that we're talking, which in our case is 4. And what do we get? -1. Boom. That is the exact data bit that Station 1 sent in the first place. It worked. It worked perfectly. The message was pulled, clean, right out of the noise. But why? How did that happen? So yeah, that wasn't just a lucky guess. The reason this works every single time is because of a really powerful mathematical property. So let's pull back the curtain and look at the magic that makes this all possible. The secret ingredient has a name: orthogonal codes. These aren't just any random strings of numbers, oh no. They are very carefully designed sequences that have a special mathematical relationship with one another. And it's this relationship that allows them to be separated perfectly, even when they're all mixed up together. And this right here, this shows you the 2 simple rules that make them so special. Rule number 1, if you multiply any 2 different codes together, say C1 and C2, the result is always 0.
They just completely cancel each other out. Rule number 2. If you multiply a code by itself, the result is simply the number of stations. So in our example, C1 times C1 equals 4.
So what's the big takeaway here? It's this. When the receiver for station 1 multiplies that jumbled, combined signal by its own code, the parts of the signal from station 2, station 3, and station 4 all mathematically just vanish. They become 0. The only part that survives is the signal from station 1. It's like everyone else in that noisy room suddenly went silent.
So this is a really elegant math trick. But why does it matter in the real world? Well, the benefits are huge. First, you get way more capacity. Since everyone can talk at once, you can cram a lot more users onto a single cell tower. This was an absolute game changer for early mobile networks. Second, it's more secure. Your conversation is basically scrambled and mixed in with everyone else's. To an eavesdropper without your code, it just sounds like static. And finally, it lets everyone share that same precious frequency band, which is huge because the radio spectrum is a very limited resource.
So, there you have it. A beautiful mathematical idea, orthogonality, solved a massive engineering problem and literally changed the way we all communicate. It really makes you wonder, doesn't it? What other invisible systems that we use every single day are being powered by similarly elegant principles, hidden just beneath the surface?